So, now in this session we are going to learn about the biasing of PN junction. So, in the previous class we have learned the formation of PN junction, and there are two currents, the diffusion current and the drift current. So, you see here, this is my PN junction, crystal diode, this is the crystal diode, and we had a junction here, this is my junction. So, we studied that at the junction there will be a depletion layer formed and there will be current from P type to N side, that will be the diffusion current, and there will be a drift current also, and both will be equal and opposite, so that there is no net current flowing in a PN junction on its own. Now, let us see what happens when we bias this crystal diode. When we bias this PN junction, then the equilibrium between the diffusion current and the drift current is disturbed. So, suppose let us first take the case of forward biasing. So, forward biasing means we connect the P side with the positive terminal and N side with the negative terminal of an external cell. So, this is the representation of a cell. This longer line means this is positive terminal and this is negative terminal. So, you see, previously let us see that this is the depletion layer, this dotted one is the depletion layer, this is the initial depletion layer. So, what will happen, this positive plate will apply a positive potential on this side, and due to this positive potential the holes from this side will be pushed, the holes, you see these holes are pushed further. This positive potential will push this hole towards the junction. As a result, this part of the junction will shift somewhere here. So, this is the junction now, this face of the junction is here. Similarly, the negative potential here will push these electrons closer to this face, and so this face will shift here. So, this shifts here. So, as a result, the previous, so this is the new position of the junction depletion layer, this is the new depletion layer. Previously the depletion layer was confined within this. So, what happens, the depletion layer is decreased when we forward bias it. So, this was the previous, so the new position of, this was the original position of depletion layer, now this is the position of the depletion layer. The depletion layer has decreased. So, what has happened, due to this forward biasing, there was previously a diffusion current in this direction, this was I diffusion, and there was an I drift. So, what has happened, number one thing, these holes from the P sides are pushed by the positive terminal of the cell, and the electrons, free electrons from this side are pushed towards. So, the junction depletion layer becomes thin, and so the drift current also increases. So, you see there is an increment in the drift current. Next point, you see, just recall the potential barrier. The potential barrier is here positive and this terminal is negative. That means in this region there is a field in this direction, there is a E barrier, electric field due to this barrier potential. So, what happens, the field in this direction is reduced because there is an external electric field, let us call this as E external. So, there is two fields now here, this barrier field and there is some E external field, E external in this direction. So, what happens, the net field will be somewhat reduced. So, net field is reduced, as a result the drift current reduces. So, not only the diffusion current increases, but you see drift current decreases also. So you see the two, there is an imbalance between these. You see the diffusion current is increased, the drift current is decreased. So there is a net current in this direction, and so the net current flows along the circuit like this due to forward biasing. This junction layer, this depletion layer is actually devoid of external charge carriers and it acts as an insulator medium. That is why, so when this becomes thin, the resistance of the PN junction becomes very less to the forward current. That is why their resistance is very less, and so the PN junction, if forward bias, conducts the current easily. So now let us see the potential barrier in the forward biased position. This is our PN junction, crystal diode, and this is the junction, this is P side and this is N side. Now I am not drawing the cell because I have to draw here, I have to show how the potential barrier is changed. So you see, I have applied positive potential to this terminal. So when I have applied positive terminal, so what happens? This pushes these holes are pushed towards this. As a result, this depletion layer is reduced, and I have applied a negative potential on this side. So these are electrons will be pushed towards this side, and so you see the depletion layer has become thin. Previously this depletion layer was somewhat up to this position. Suppose this was the position of the depletion layer initially, and now this position. So this is new position, that is the new width of the depletion layer. And so what happens? So here the depletion layer is this. If I draw the potential barrier, one more thing, we will compare the potential barrier initial and final. So now you see here, this potential barrier is here like this. This is the barrier potential. So here the potential, suppose I say this potential here to here is 0 or something, then it is going to be negative here, and then the potential changes. So this is the potential difference between these 2 points. So the barrier potential is this much, and you see this is the barrier potential after biasing, and this, you see, depletion layer initially is here. So here this potential barrier was this much. This is your barrier potential before biasing, means there is no biasing, then this is the barrier potential. So you see here, when you bias this forward bias, the depletion layer has decreased from this to this, and you see this barrier height is reduced this much. So the potential barrier is reduced here. So as we increase the bias voltage, this depletion layer will decrease, has decreased, and the potential barrier has been reduced. So you see the initial potential barrier was very high like this, now it is reduced to this. The potential barrier for silicon is nearly 0.7 electron volt and for germanium is 0.3 electron volt. So what happens when we apply the forward bias and increase it slowly, initially the current will be very less, but once suppose it is silicon, it becomes 0.C, then the net field at the junction becomes 0, and so current conduction will increase, and once this external bias is more than 0.7, then the current will be continuously and linearly increasing. Let us see with the help of a diagram, and let us summarize what happens in the forward biasing. So you see, let us summarize our result. This is our crystal diode, this is the junction P type and N type. When I connect it with the positive type and this with the positive terminal of the cell to P type and this to the negative, it becomes forward biased. So when the P side of a crystal diode is connected to the positive terminal, and N side to the negative terminal, then we say that the crystal diode or the PN junction is forward biased. This is the meaning of forward biased. The positive potential applied at the P side pushes the holes towards the junction, and the free electrons are pushed towards the junction by the negative potential of the external cell. So as a result, the depletion layer becomes thin. This is important point. Depletion layer becomes thin and the potential barrier gets reduced. This also gets reduced. So two important things. The resistance of the diode becomes less, and so it conducts the current very well. So once that barrier is reduced, then current will continuously and linearly flow. Please take this down. Now let us draw its graph. We will draw the graph with current on the y axis and the voltage measured in volts along x axis. So, now what we observe that this current, the order of current is in milliamperes, and we observe that initially the current does not increases very well and then it increases linearly. This is 0.3 if it is germanium, and for silicon the graph is something like this, and this is 0.7 volts for Si. This is for germanium. So, initially the current does not grow too much because the barrier potential is here something like this. This is the potential barrier. So, at the junction we have two fields. This is E due to barrier and E due to external. So, till this external field balances this field, reduces this net field to 0. So, this is called knee voltage, knee voltage. So, at this stage, before this stage, this barrier field is more than external field, but here this field becomes equal to this field and the barrier is net field is reduced at the junction. Thereafter, this barrier field is less and this field is more, and so as a result the current, this becomes a conductor and the current grows linearly, where Ohm's law can be followed. It will, the resistance here R, that is forward resistance, R is equal to V by I, that is we will take the V by I means this slope of, not this curve, the slope of this curve will be I by V. If we calculate this R V by I, then we will get the resistance offered by this diode to the forward current. This resistance is very less, and it is something 1 to 50-100 ohms like that, maybe within 1000 ohms, within 1000 ohms, 1 kilo ohm, it will be within 1 kilo ohm, something like that. This is how current varies in the forward biased crystal diode. Now, come to reverse biasing case. In reverse biasing, this is our crystal diode, this is the junction, and we have P type and N type. What we do, we connect it P type with the negative terminal minus and N type with the positive terminal of an external cell. This is an external cell. Now, the negative potential applied here will pull these holes towards it. So, this is the dotted position of the depletion layer initial depletion layer. Now, when you pull these holes towards this end, P side, then what happens? This shifts this way, and the depletion layer, this face of the depletion layer comes here. Similarly, the electrons are attracted, pulled towards this side by the positive terminal, the positive potential of this, and so this junction, this side shifts at this location. So, depletion layer here increases. Thus, you see depletion layer is increased. So, let us remove this now. This was the previous position, and now this depletion layer has been increased. What about the field? Initially the field was in this direction and we used to say E barrier, and now my external field is in this direction, E external. So you see here the electric field at the junction has been increased. So what happens? Previously this was the I diffusion. So when there was no biasing, there was I diffusion and there is I drift. I diffusion and I drift. Diffusion. Both were equal. Now when I have reverse biased it, then what has happened? These holes has been pulled this way and electrons this way. So the junction depletion layer increases and so the diffusion current is decreased. So now it is shortened. Also the electric field here, junction field has increased. As a result, the electron hole pair created here. So since this electric field is increased, so the current density is defined as NEVD, or simply I want current J is equal to sigma E. So if you see electric field net has been increased, so there will be more drift current. As a result, drift current will also increase. So not only this diffusion current decreases and this drift current increases. Now since there is again, you see there is an imbalance in the drift current and the diffusion current, so there is a net flow current in this direction. There is a net flow of current in this direction. You see one more thing, this net flow of current is because of this drift current. This drift current is exceeding this diffusion current. Now we know that this drift current is due to the minority charge carriers, the electron hole pair created at the junction. So the order of this drift current is very small. So what has happened? Let us summarize. What has happened? This depletion layer has increased. The net field here has increased. So there is an imbalance in diffusion current and drift current. So there is a net current flow in this direction, and the current flow is because of minority charge carriers, which is very small, whereas in the forward biasing I diffusion were more than this, but I diffusion is due to diffusion of majority charge carriers. The order of current there is very large, that we saw it is in milliamperes, and here it is in microamperes or nanoamperes depending on the nature of the PN junction. Let us summarize these points, and first we will see how the potential barrier changes. So now let us talk about the depletion layer during reverse biasing. So this is my P type and this is my N type. We have applied a negative potential on this P side. As a result, these electrons, these holes are attracted towards this, and so this initial position of this depletion layer was here, now it has moved here. And similarly here, these electrons are attracted by the positive terminal, the positive potential of the external cell, which I am not showing. So this shifts here. So now this is the new depletion layer, and previous depletion layer was this old depletion layer, and this is new depletion layer after biasing. So you see here, this is old. So the junction, at this junction, what is there happening? This is the negative, and here you see this is positive. So this is the situation of the potential barrier at the junction. So the situation here is before biasing, and you see here after biasing what happens, the barrier is, you see that width increases, so barrier starts here only, and so this is negative, and you see this is what? This is positive, negative. So this is after after reverse biasing. This is after reverse biasing, before. This is the situation of the depletion layer. Now, this is here minus and this positive. Here this is actually the graph of not the potential but the electric field. I am talking about electric field, the field due to the barrier. So, here this is the charge distribution. So, you see here when I say it's minus, that means here the space charge, this is in fact the graph of space charge region. So, here some negative charges is there and some here positive charges is there. And so, what happens? So, when you pull these holes here, the space charge region here and here will become more, and more will be the potential barrier. That can be shown by another diagram. So, this graph is for actually the charge distribution. If I actually want to show in terms of potential, we can use another graph which we have done in our explanation of PN junction. So, you recall our previous session where I have used this graph to tell how the charge distribution, space charge distribution takes place. So, just imagine with the help of this graph, suppose I consider this initial distribution, then this here you see this is minus more. So, more charge is here, more charge is here, negative, positive, and as I go here the charges is less, few charges, but here the more and more charges will be at the junction, and here you see something like this according to this graph. Suppose it's not I am not saying that this is the actual graph may be like this sinusoidal, depending on the nature of charge distribution at the junction will actually depend on the nature of PN junction. So, this whole region will become space charge. So, previously before biasing you see the charge was within this and it is given by this, but when after biasing this charge is given like this. You see this curve may be something like this or maybe something like this. That means we say that the charge is uniformly distributed here and here, and here it is like this, and this is something uniformly uniformly negative charge and here. So, there are different ways, and it will depend on the nature of PN junction that how the charge is distributed here. So, is any of these representation for this is okay. Now, suppose I want to define the potential, that how potential varies during. So, you see this is the initial potential variation. Suppose this is the initial potential variation. So, you see the depletion layer starts from here and up to go to here, and this is the barrier potential, V barrier. So, you see here this is P type and N type. Here the potential is nearly the same. As you go on, the potential increases and then the potential is uniform. So, this is when this is the depletion layer is within this region up to here to here. So, this is normal. Now, if I forward bias it, then the depletion layer decreases. So, suppose depletion layer starts, it decreases up to here only. So, this is the new position of, this is the new width of depletion layer, and the barrier is also reduced, V barrier during forward biasing. So, this is the example for this in terms of potential. Now, if I say reverse biasing, then you see this width also increases. This width also increases. The width is this much width. So, this is the initial width without any biasing. This width is during reverse biasing, and this width is during forward biasing, forward width. And you see from here during reverse biasing during forward biasing the potential barrier is this, and this is under no biasing, and this is under reverse biasing. This is the potential at different, how the potential is increased this way. Now you see again, this is the potential I have plotted for a positive charge. Generally we talk about electron, so all these graphs can be drawn in this way. If I talk about the potential of a electron, that how the potential of electron will be at different regions in the p-n junction. Let us summarize the whole reverse biasing now. So now let us summarize the ideas we developed with reverse biasing. So this is the state of reverse biasing, that we have a p-n junction diode, and when we connect this p with the negative terminal and n with the positive terminal, we say it is reverse bias. So what happens, the depletion layer you see has increased. So in a reverse bias, the p side is connected to the negative terminal of an external cell, and n side is connected to the positive terminal of the cell. So this is what we do in reverse biasing. The electrons, the free electrons from the n side is attracted by the positive potential applied to it, and the holes in the p side are attracted towards by the negative terminal applied to it. As a result, the depletion layer width increases. Important point. The junction barrier potential increases. The resistance of the crystal also increases. You see, the resistance is largely of this region. Since this region width is increased, so is the resistance increases. It is nearly tens of thousands of times more than the resistance in the forward biasing position. It is nearly 50,000 to lakhs, tens of thousands. It is nearly tens of thousands of times, that of forward resistance. That is the resistance during forward bias. So this resistance is lakhs times, 50,000 times, lakh time, 1 lakh time more than the resistance during the forward bias. Please take this down and then we will see the order of current and the graph, how reverse current varies with voltage. Now, due to reverse biasing, the diffusion current gets reduced. Since you see the holes are pulled this way and the electrons are pulled this way, so they diffuse less easily, so the diffusion current gets reduced. Now the net field at the junction is the sum of the barrier field and the external field which is same during reverse bias. This is important point. During reverse bias, the field is same. What field? At the junction, you see this is the junction depletion layer. This is the E barrier. Field due to this barrier charges, and you see this is E external. So the total field is the sum of these two fields and are in same direction. Thus the drift current is more, and thus the current flowing is due to the transport of the minority charge carriers. The order of this current is very low, from microamperes to nanoamperes. That depends on the PN junction, whether it will be in microamperes or nanoamperes. So the current is very small. Now let us draw the graph. Please take down this first. So now let us plot the graph. So this graph for reverse bias is plotted along this. This is minus V, the volts, that is measured in volts, and here this reverse current IR. So we see that initially the here V is in the current is like this. So almost the current begins to flow at a very small reverse bias voltage also. The current begins to flow, but this current and then soon it becomes saturated. I saturated. So this begins, the current begins to flow, even a small reverse bias is there. Unlike in the previous case of forward bias, unless it becomes 0.7 for silicon, the current is very less, but here the current begins to grow immediately, no need of 0.7, 0.2, 0.3 like that, and then it becomes saturated. So the order of current, saturation current will be of, suppose this current is in microamperes. Suppose I say 1 microampere, this is minus 2 microamperes, then minus 3 microamperes, like that dot. And here the voltage varies, it can be varied to any extent. We will see later on that the current will increase, begin to increase like this. Presently we are not interested in this part. So the current becomes saturated with once within a very small range. So in negligible range, that means if I start from 0 to increase voltage, the current will immediately become saturated. So here no appreciable voltage is required like there for silicon 0.7, for germanium 0.3 in reverse bias. The order of current is important, it is in microamperes, and for reverse bias it is in milliamperes. This is your current plotted here, forward current. This is your reverse bias, VR, minus VR. Now let us see the IV characteristics of a PN junction diode. So in order to study how the current varies with the voltage of a PN junction diode, we will use different circuits for this forward bias and the reverse bias. So let us take forward bias. So you see the symbol, first of all let us see the symbol used to denote a PN junction is like this. A PN junction is like this. So when a PN junction is like this, that means this is P side and this is N side. This is P side and N side. Why we use this symbol, I will explain later on. So this is the PN junction, and the voltage which is here, that can be measured with a voltmeter. This is the voltmeter connected. And now we connect a milliammeter here to measure the current. Now this is your forward biased. So P should be connected to positive terminal and this. And now you see this indicates that we have connected a potentiometer or rheostat to vary this voltage. This is voltmeter, and this arrangement is for forward biased. So forward characteristics. So to study forward characteristics, we use this type of circuit. Next is we have a PN junction here, same diagram. This voltmeter is again the same, we have to use the same voltmeter, but here this is microammeter, and then you see the cell should be connected reverse biased. So reverse characteristic, and this is forward. So this is again the varied. So in order to study the forward characteristics, we have to use this circuit. If we have to study reverse characteristic, we have to use this circuit. This is PN junction, this side P and this side N. So you see this P is connected to the positive terminal, and so this is your forward biased and this is reverse biased. The order of current measured is here microammeter is used and here milliammeter is used. Here voltmeter is normal with 1 to or 0.1 to 100 volts also you can use. 0.1 to something 10 volts also here you can use, here up to 100 also we can use. We will see why we have to use it. So now come to forward characteristics. Forward characteristics. The graph, the plot of graph between the current, the forward current and the external potential applied is called forward characteristics. Forward characteristic. Now here we plot a curve. Here this is current in milliamperes and this forward voltage. So what we observe, initially there is no increment in current, and once the current becomes, this is called knee voltage, knee voltage. So it is 0.7 volts for silicon, 0.7 volts for silicon. This is forward voltage. Then the graph becomes nearly linear. If I take a point here and then I calculate VA, and for which there is a corresponding current A, then we can define as DC forward resistance. Its symbol will be R forward DC. DC will be VA by IA. And we have AC forward resistance. Forward resistance is equal to R forward and AC as delta V by delta I. So this is how we can define the resistance of the diode when it is forward biased. So we require this data when we have to operate this in forward biased. So you see this for forward biased, this graph is linear here, and this is 0.6 volts, and this suddenly it becomes here like this. So you see it's not decreasing, it saturation something like this, and then it goes abruptly. So this voltage, let it be rising suddenly. So the voltage corresponding to this is called breakdown region. Breakdown voltage. This is under reverse, this voltage is. Now you see here, let us do one thing. I will draw this diagram to tell that. So this happens at a large voltage. So you see it's 0.7, suppose it is 0.1, 0.2, 0.3, 0.4, 0.7, then 10, 20, 30, 40. So the scaling is not uniform. So at a very large, you go this very large. So I have shown that this is at a very large distance. So discontinuity is there in this line. So to just this line to tell that this graph is very large and this happens as a large distance. That means at a large voltage compared to this voltage, that is, you see here 0.7, but this is not 0.7, this is nearly 40, 50, 75, even have 20 volts. So depending on what is the usage of this breakdown voltage is different for different diodes. So this is breakdown voltage. Now you see the diode when used in forward region here will have a resistance. So the resistance here, if I draw the slope, you see this will be delta I and this will be delta V. So the resistance will be R is equal to delta V by delta I. Here you see delta V by delta I is very small. So a small resistance. So forward resistance means small resistance. Small resistance. And what about here? You select a point here and a point here. You just see the difference. Just see the difference. This difference is very small. This difference is very small. So this is delta I and the corresponding voltage is delta V. So, you see delta I is very small. So, this resistance is tens of thousands of times more than the resistance during forward bias. That is why during forward biasing the crystal conducts very well, and thus during reverse biasing it does not conduct at all. The current is very small. So, often this so small current is so small that it cannot be detected by our instruments, and we say the current is 0. So, thus a diode conducts very well under forward bias and very poor along under reverse bias. Thus, it is a device which conducts only in one direction. So, thus it is a unidirectional conducting device. Unidirectional conducting. So, what we do in order to describe it, we use a symbol like this. The symbol means that if you allow a current to go along this direction, it will allow it, but if you allow a current in this direction, it will stop it. So, this is the meaning of that symbol. That is why we selected this. So, when current is going this side P and this side N. So, this line means it stops currents from that direction, and arrow means it allows the current to go in that direction. So, the unidirectional current conducting property of a diode can be used for rectification, that is converting an AC into an DC, which we will see in the next session.